Hello and welcome everybody to today's lecture on the gamma function. Specifically, this is going to be a lecture that addresses the development of the integral version of the gamma function, which is probably the form that most people are familiar with, but very few sources that I've found actually derive it. So that's what we're going to do here. But first, recall n factorial, if you remember from high school algebra or probability, is equal to n times n minus 1 times n minus 2. You basically reduce the value of the integer every time, multiplying all the way down to 1 for n a positive integer. Right, so this definition only works if we're starting out with a positive integer. For example, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1. That's how the factorial was originally conceptualized. And so what we can do is we can actually graph the factorial of these different positive integers on our xy coordinate system. I'll make a little chart over here with n and n factorial. So if n equals 1, n factorial is 1, so I'm going to graph 1, 1 there. 2 factorial equals 2. I'll put that down there. And then 3 factorial will equal 6. You can see this actually increases very rapidly. Then 4 factorial equals 24. That's going to be somewhere up there. And so then the natural question emerges, is there some line we could draw representing a function that would interpolate at all these intermediate values? In other words, there's an infinite number of ways of connecting these dots. We would want our interpolating function to include something we can readily deduce, which is that 0 factorial equals 1. And it might also define the factorial for negative numbers as well. We don't know yet what this graph should look like. This is just a guess. In fact, on the negative x-axis, it's wrong. But the question remains, is there a more general function that extends the factorial beyond integer inputs, beyond the positive integers? That's what we're looking to do here. So Euler's initial approach to this problem of extending the domain of the factorial function led him to consider first infinite products. I talk about this at length in my previous video, how Euler developed first an infinite product definition of the factorial function. And namely, Euler found that n factorial can be shown to equal the limit in the infinite product as m approaches infinity of m factorial, not n, m factorial times m plus 1 to the power of n all over n plus 1 times n plus 2 times n plus 3 dot, 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 all the way up to n plus m, which I'll write out here. In other words, if we plug in any n that we wish, except for a negative integer, this will give us a result which can be shown to be equal to n factorial. So this infinite product formula for the factorial function extends the domain. Now we don't have to limit ourselves to merely the positive integers, but we can also consider positive and negative fractions as inputs here. And when we do that, for example, we get some amazing results. We find that 1/2 factorial equals 1/2 times the square root of pi. Very cool. You'll have to watch my previous video to see how that's done. We find that 0 factorial actually equals 1. Negative factorials also are developed there, and so negative 1/2 factorial equals radical pi. And you'll, again, see my previous video for how we actually prove all that. But we're going to rely on that information to move forward here, because Euler noticed that 1/2 factorial squared, well, that would equal 1/2 times the square root of pi, quantity squared, and that equals pi over 4. Well, as soon as we see pi over 4, we should be thinking maybe about circles, and specifically, this pi over 4 could be thought of as the area of 1/4 of the unit circle. So once we start thinking about this a little bit more geometrically, let me draw this. So there's our unit circle, okay, in green, and I'll just lay down some coordinate axes here. I'm doing that now. And of course, our radius equals 1. It's a unit circle. And this pi over 4 could be thought of as representing this area of 1/4 of the circle. So that area there would equal pi over 4. Well, as soon as we're looking at areas under curves, we should be thinking about integrals, and that's exactly what Euler did. He went on to investigate whether the factorial function could be expressed in an integral, whether it could be expressed as an integral, instead of just as an infinite product. So that's what we're going to derive now in the rest of this video. So again, our goal is to find an integral expression such that n factorial is the integral of some function f of x dx. And perhaps I should have written f of x comma n, because obviously there should be some dependency on n here. And our limits of integration are a and b right now. We haven't figured out what those will be yet. But here's our starting point. I'm going to draw the unit circle again, and I'm putting down some axes for us. Okay, and again, that's our radius equal to 1. And I'm going to just shade in yellow the area we're looking at. Those are our x and y axes. And now I'll write the equation for this circle in terms of x and y based on the Pythagorean theorem, and that it's a unit circle. X squared plus y squared equals 1. So now we'll solve for y. Y would equal the square root of 1 minus x squared. And again, we're going to rely on the fact that 1/2 factorial squared equals pi over 4, which is the area of 1/4 of this unit circle, or we could think of it as the area under the curve. So if it's the area under the curve, then I can write it as the integral from 1 to 0 of the square root of 1 minus x squared dx. And now I'm going to do a u substitution. Let's let u equal x squared. Then du dx equals 2x. We're flipping that around. Du over 2x equals dx. Okay? But also, if x squared equals u, that's our u substitution, then x equals the square root of u. So we can write du over 2 radical u equals dx. Okay, so with those simplifications in mind, I'm going to rewrite this integral. So we have 1/2 factorial squared equals pi over 4, which equals the integral from 1 to 0 of the square root of 1 minus u du over 2 radical u. And now I'm just going to write this in terms of exponents instead of with radical signs. So that will equal 1/2, I'm just pulling that out from the integral, times the integral from 1 to 0 of 1 minus u to the quantity 1/2 times u to the negative 1/2 du. And again, this integral expression equals 1/2 factorial squared. This expression suggests there might be a relationship between the factorial function and integrals. So Euler used that as his starting point. He began by considering more general integrals of the form integral from 1 to 0 of 1 minus x to some power, which we can call n, times x to some other power, which we'll call c, dx. And perhaps the most natural thing to do when confronting this kind of an integral, where you have 1 minus x to the n times x to the c, is to do an integration by parts. Right? We have one function in x and another function in x that are being multiplied together in this integral. So I'm just going to review what this is. If you're given one function of x, let's call it u of x, and some other function of x, which we'll call v of x, and we have an integral of the form, the integral from, let's say, b to a of u dv, then that integral is always going to be equal to u times v, evaluated at those boundaries, so evaluated from b to a, minus the integral from b to a of v du. And in the video I have posted on my channel on Taylor series, I derived that identity. But let's apply this here. So let's let u equal 1 minus x quantity to the n. And then by differentiation, du dx will equal n times 1 minus x quantity to the n minus 1. That's just making use of the power rule for derivatives. But let's not forget that 1 minus x is a function that we have to differentiate. Also, that just equals -1, and that's applying the chain rule there. So our derivative du dx equals n times 1 minus x to the n minus 1 times -1. So du equals -n times 1 minus x to the n minus 1 dx. So let me put a box around that here. So that's our du. And then we're going to let our dv equal x to the c dx. So that's that part of the integral there. And then we'll integrate both sides. So we get the integral of dv. I'm writing that here. The integral of dv equals the integral of x to the c dx. And so we have v equals x to the c plus 1 over c plus 1. That's the power rule for antiderivatives. And I know that some of you are wondering, where's the constant of integration? When you do integration by parts, that drops out of it, so I don't have to worry about that here. So there we have it. That's our du and our v. And again, here's what we've got. This is our integral. 1 minus x to the n times x to the c dx. And for our integration by parts, that's our u there, 1 minus x to the n. X to the c dx is our dv. And we're saying u equals 1 minus x to the n. And then we found that our du then has to equal -n times 1 minus x to the n minus 1 dx. Our dv we set equal to x to the c dx. And we found that our v then equals x to the c plus 1 all over c plus 1. And so when we plug all of this in, remember that this is going to equal u times v, evaluated at the boundaries x equals 1 and x equals 0. So this will be 1 minus x to the n, that's our u, times x to the c plus 1 over c plus 1, that's our v. Evaluated at those endpoints x equals 1 and x equals 0. Minus the integral from 1 to 0 of v du. So this will be minus the integral from 1 to 0 of x to the c plus 1 over c plus 1 du, which we have as -1 times n, times 1 minus x to the n minus 1 dx. So let's do this integration by parts. So plugging in our values at the endpoints there, so we'll have 1 minus 1 to the n times, plugging in 1 for x again, 1 to the c plus 1 all over c plus 1. But 1 minus 1 to the n is just, of course, 0 to the n, so that entire term actually cancels out and equals 0. And then at the other endpoint, we have 1 minus 0 to the n times 0 to the c plus 1 over c plus 1. And we can see, because of that 0 there, that this whole term also equals 0. So that takes care of the first part of the integration by parts. And now over there in that integral in the second part, I'm just going to pull out these constants. So I have minus -1 times n over c plus 1 times the integral from 1 to 0 of 1 minus x to the n minus 1 times x to the c plus 1 dx. So that just equals, with the double negative canceling out, n over c plus 1 times the integral from 1 to 0, 1 minus x all to the n minus 1 times x to the c plus 1 dx. So I'm going to put a box around this here. Let's put a box around this. I'm just putting a box around this because that was a lot of work and I want to collect these results. This is an important intermediate step for us. So I'm going to pull that up to the top of the screen. Again, we found after one round of integration by parts that the integral on the left equals the expression on the right. Now this expression on the right can also be integrated by parts, right? We have the product of two functions of x there. So let's integrate by parts again. And here I'll skip some steps because it's a very similar process to before. We'll let u equal 1 minus x now to the n minus 1. And then du will be found to equal negative n minus 1 times 1 minus x to the n minus 2 dx. We're going to let dv equal x to the c plus 1 dx. And then we'll have that v equals x to the c plus 2 over c plus 2. Now when we plug in those values and do this integration by parts, what do we get? We'll get n over c plus 1, that's a constant outside of the integration, times, this is our u times v, so this is 1 minus x to the n minus 1, times x to the c plus 2 over c plus 2, evaluated again at the boundaries, evaluated at x equals 1 and x equals 0, minus the integral of v du, so minus the integral from 1 to 0 of x to the c plus 2 over c plus 2, times negative 1 times n minus 1 times 1 minus x to the n minus 2 dx. And I'm just going to close brackets around that expression there. And so when we do this, we'll find that that first term again evaluates to 0 when we plug in x equals 1 and x equals 0 at the boundaries there. And so we're left with n over c plus 1 times c plus 2, that's in the denominator in our integral. And then here I have an n minus 1 term, which is also a constant I'm going to pull out, so that comes out there, times the integral from 1 to 0 of x to the c plus 2. But actually, let me erase that. I want to write the 1 minus x to the n minus 2 first. I'm just switching the order of multiplication here. Okay, so then times x to the c plus 2. I think you guys will see why I did that in a second, dx. And I hope you guys can see that there's a pattern to this. And to see how this ultimately works out, if we were to plug in some numbers, let's plug in n equals 3. Pick a nice small number for n just to see where this is going. So here's what we have so far after doing 2 rounds of integration by parts. And then if we plug in n equals 3, we get the integral from 1 to 0 of 1 minus x to the 3rd power times x to the c dx equals 3 times 3 minus 1, which is 3 times 2, over c plus 1 times c plus 2 times the integral from 1 to 0 of 1 minus x quantity to the 3 minus 2, which is just 1, to the x to the c times x to the c plus 2 dx. And then we just have to do one more round of integration by parts to see what this integral ultimately equals. So letting u equal 1 minus x to the 1st power, we'll then find that du equals negative 1 times 1 minus x to the 0 dx. In other words, du just equals negative dx. And then dv is going to equal x to the c plus 2 dx. So our v equals x to the c plus 3 over c plus 3. So you've seen me do this integration by parts a couple times, so I'm going to just go through it quickly here. This is going to equal 3 times 2 times 1 over c plus 1 times c plus 2 times c plus 3, all times the integral from 1 to 0 of x to the c plus 3 dx. Well, now I'm going to just write that 3 times 2 times 1 as 3 factorial. And that's really the whole point of us doing this integration. So we've got 3 factorial now coming out of this over c plus 1 times c plus 2 times c plus 3 times x to the c plus 4 over c plus 4. That's what you get when you do that integral, of course. Evaluate at the boundaries, x equals 1 and x equals 0. So we're getting somewhere, right? We've got 3 factorial in the numerator there over c plus 1 times c plus 2 times c plus 3. And this is being multiplied by the expression x to the c plus 4 over c plus 4, evaluated at the boundaries, evaluated at x equals 1 and x equals 0. I'll just close the brackets here, make that very clear. So this is going to equal 3 factorial over c plus 1 times c plus 2 times c plus 3. And then inside the brackets, what do we get? We plug in 1 for x there, 1 to the c plus 4 over c plus 4, minus, plugging in 0 here, 0 to the c plus 4 over c plus 4. Well, that second term there, that just equals 0, so I'll just cross it out. That's 0. And this is going to equal then 3 factorial over what? Well, that 1 to the c plus 4 is also going to just equal 1. The c plus 4 survives there in the denominator, so I get c plus 1 times c plus 2 times c plus 3 times c plus 4, all in the denominator of this final expression. So let's put a box around that. That's what we have. So that was for the case of n equals 3, but we can also see from this what's going on in general. In general, what we have is that the integral from 1 to 0 of 1 minus x quantity to the n times x to the c dx, that equals n factorial, right? N factorial, all over c plus 1 times c plus 2, and so on, dot, 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 all the way up to c plus n times c plus n plus 1. Right? In our n equals 3 case, the last term in the denominator there was c plus 4. So this integral almost gets us to the factorial that we desire, right? It almost gives us an expression for the factorial, except for one thing, except for those terms involving c in the denominator. So what is our goal going to be? Our goal is going to be to somehow isolate the numerator, which was n factorial in that expression. And we're going to have to manipulate the integral a little bit to get there. So again, we're going to isolate the numerator in this expression that we have here, which is the integral from 1 to 0 of the quantity 1 minus x to the n times x to the c dx. And again, that equals n factorial over c plus 1 times c plus 2, and so on, dot, 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 all the way up to c plus n plus 1. And here was Euler's idea for how to isolate that numerator. We're going to treat the constant c as the ratio of 2 other constants. So we're going to let c, our constant c, equal the constant f over g. And you'll see why we're doing that in a moment. So now I'll rewrite the integral with that substitution. So again, the integral from 1 to 0 of 1 minus x to the n times x to the f over g dx, and that's going to equal n factorial all over, now substituting f over g for c, f over g plus 1 times f over g plus 2, and so on, all the way up to f over g plus n plus 1. Now when we look at this denominator here, we have n plus 1 terms in that product. So what we're going to do to simplify this is multiply the right-hand side of the equation by what one of my former math teachers called a creative form of 1. We're not changing the value of this expression, we're just multiplying it by 1 in a very clever way. We're going to multiply it by g to the n plus 1 over g to the n plus 1. So let's do that. We're going to multiply this right-hand side by g to the n plus 1 over g to the n plus 1. So when we do that, in our numerator, we just end up with n factorial times g to the n plus 1. But in our denominator, something very nice happens. We had n plus 1 terms in our denominator, and we're multiplying it by g to the n plus 1. So each g takes care of the terms in one of those binomials. So for example, the first one becomes f plus 1 times g. The second term becomes f plus 2 times g. Each of these terms can be thought of as multiplying by a g, which then distributes, and it cancels the g in the first term in that binomial, which was f over g, and it multiplies the second term. So our last one will be f plus n plus 1 times g. Okay, so there we have it. Now we're going to make a couple slight rearrangements. I'm going to bring a couple things to the left-hand side of the equation. First, I'm going to multiply both sides of the equation by f plus n plus 1g. I'm just bringing that last term in the denominator over to the left-hand side. And I'm going to divide both equations by g to the n plus 1. I'm taking that out of the numerator on the right-hand side and putting it over on the left-hand side. And this is going to multiply by our integral, the integral from 1 to 0 of 1 minus x to the n times x to the f over g dx. And that, of course, is going to equal now n factorial over f plus 1g times f plus 2g dot, 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 all the way up to the penultimate term, which was f plus ng. Now it'll become evident why we made that substitution of f over g in place of c, because we're free to experiment with what we want f and g to equal. In fact, if we tried setting f equal to 1 and g equal to 0, well, let's see what happens. On the left-hand side, we'll get 1 plus n plus 1 times 0 all over 0 to the n plus 1. And that looks a little problematic, but we'll deal with it. Times the integral from 1 to 0 of 1 minus x to the n times x to the 1 over 0. Okay, also looks problematic, but bear with me. Dx equals n factorial all over 1 plus 1 times 0 times 1 plus 2 times 0, and so on. Here's where this is paying off, all the way to 1 plus n times 0. In other words, every term in the denominator there just equals 1. So I'm going to cancel those all equal 1. So we can now say this expression equals n factorial. But we can't declare victory just yet because of these terms where I have 1 over 0, first as a leading coefficient, and then as the exponent of x in the integral. Those terms are undefined. But we're not going to give up. Euler is clearly on the right track here. Maybe we can make some adjustment to our integral so that we can better see what's going on the left-hand side of the equation and actually evaluate that left-hand side as a limit. Well, we'll get there. But for now, I'm going to rewrite the integral again using u instead of x as my dummy variable for integration, because I'm going to make a substitution to simplify that integral in just a moment. So here we go. We're going to write the integral from 1 to 0 of 1 minus u to the n times u to the f over g du. And now here's the brilliant substitution Euler came up with. We're going to let u equal x to the g over f plus g. It shouldn't be intuitively obvious why we're doing that, but it will simplify things tremendously. du dx then will equal g over f plus g times x to the g over f plus g minus 1 in the exponent there. Let me put parentheses around that exponent. So now solving for du, in the exponent, I'm going to let that minus 1 equal f plus g over f plus g. So I'm going to get g over f plus g times x to the g over f plus g minus, and that 1 there again is going to be f plus g over f plus g. I'm just finding a common denominator there. And then what is g minus f plus g? That's just minus f. So it's going to be x to the minus f over f plus g. So let's summarize what we have so far with this substitution. We have the integral from 1 to 0 of 1 minus u to the n times u to the f over g du. And once again, we let u equal x to the g over f plus g. Now let's take a look at our bounds of integration. Make sure those haven't changed. At u equals 1 in the integral there, x would also have to equal 1. And at u equals 0, x will also have to equal 0 for that substitution to work. So the bounds of integration actually aren't changed by this variable substitution. We still have the bounds of integration being 1 and 0, and that's good. The other piece of information we found is that du is equal to g over f plus g, g over f plus g, times x to the minus f over f plus g dx. So now I can rewrite my integral as follows. The integral from 1 to 0 of 1 minus x to the g over f plus g, that's my variable substitution right there, close parentheses, to the n times, again subbing in, x to the g over f plus g all to the power of f over g. And then for my du, I have the substitution worked out already. My du is going to equal g over f plus g times x to the negative f over f plus g dx. Now that g over f plus g is just a constant here, so that can get pulled out to the front of the integral. So this will equal g over f plus g times the integral from 1 to 0 of 1 minus x to the g over f plus g, all raised to the power of n. And for the next term, I have x raised to some power raised to another power, so I can multiply my exponents. The g's cancel, and I get x to the f over f plus g. And then at the end here, I get x to the negative f over f plus g dx. Well, those two last terms, x to the f over f plus g and x to the negative f over f plus g, those will just multiply out to x to the 0, which equals 1. So that's the beauty of this simplification that Euler came up with. I end up with g over f plus g times the integral from 1 to 0 of 1 minus x to the g over f plus g all to the power of n dx. So now we can start to put it all together. Remember, we did a lot of work already on that integral before we did the variable substitution. We found that f plus n plus 1 times g all over g to the n plus 1 times the integral from 1 to 0 of 1 minus x to the n times x to the f over g dx equals n factorial over f plus 1 times g times f plus 2 times g dot 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 all the way up to f plus n times g. This is the step we reached before trying to let f equal 1 and g equal 0 and getting n factorial on the right-hand side, but those indeterminate forms on the left hand. So then we rewrote u for our dummy variable in place of x. So we put a u there where the x's were. I'm just doing that here. And then we made this very important variable substitution. We let u equal x to the g over f plus g. Now, with that substitution having been made, the integral reduces to g over f plus g times the integral from 1 to 0 of 1 minus x to the g over f plus g all to the power of n dx. And now we're going to combine these two facts. We're going to keep that leading coefficient we have in the expression up top, f plus n plus 1 times g over g to the n plus 1. But now we're going to write our new form of the integral, starting with g over f plus g. Remember, we pulled that out from the integral because it's a constant, times the integral from 1 to 0 of 1 minus x to the g over f plus g, closing parenthesis. This is all being raised to the power n dx. That again equals n factorial over f plus 1g, close parenthesis, times f plus 2g, and close parenthesis again, and so on, dot, 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 up to f plus ng. And this is good for us because now we can start to actually simplify this integral. So to simplify the integral, we don't have to do too many complicated things. Most of the hard work is already behind us. But again, we have f plus n plus 1g all over g to the n plus 1 times g over f plus g times our integral from 1 to 0, 1 minus x to the g over f plus g, close parenthesis, all to the power n dx. And I'd just like to make a few observations here. First of all, the f plus g that we have there in that expression, that could be set equal to f plus g to the n plus 1 over f plus g to the n. And it'll be convenient to make that change in just a moment. We can write our integral in the following way: f plus n plus 1 times g over g to the n plus 1 times g over, and here it is, f plus g to the n plus 1 over f plus g to the n. I'll put some parentheses around that to keep that as one term. This is, again, times our integral. 1 to 0, 1 minus x to the g over f plus g to the n dx. Now I'm just going to make some easy cancellations. I'm going to cancel the g in the numerator there, and that's going to cancel a g down there in the denominator, so that term will just become g to the n. And then this will equal f plus n plus 1 times g. And now what I'm going to do is I'm going to take that f plus g to the n plus 1 in that second term, and I'm just going to switch it around. I'm going to put it in the denominator there, just taking advantage of the fact that multiplication is, of course, commutative. So then my g to the n will be here. I've just switched those two terms. I've just switched their order for convenience. And then I'll still have f plus g to the n right down here. I'll put some parentheses around that expression. And then this will, of course, multiply our integral, which I haven't changed, the integral from 1 to 0 of 1 minus x to the g over f plus g, close parenthesis, all to the n dx. Now, looking at this term here, I can take the exponent to the nth power and just put it outside the parentheses. That'll be convenient. And then I'm going to actually take this constant and I'm going to bring it inside the integral. And why I'm doing that will become clear in a moment. We'll have f plus n plus 1 times g over f plus g to the n plus 1 times the integral from 1 to 0 of 1 minus x to the g over f plus g raised to the n, all over, here it is, g over f plus g, again raised to the power of n, dx. And now again I'm going to just put a big parentheses around both of these terms. They're both being raised to the n, so I can put it outside the parentheses there. So with all of these adjustments we've made to our integral, let's try again setting f equal to 1 and g equal to 0. And you'll see that the hard work is going to pay off. We're going to get 1 plus n plus 1 times 0 over 1 plus 0 to the n plus 1 times the integral from 1 to 0 of 1 minus x to the 0 over 1 plus 0 all over 0 over 1 plus 0, close parenthesis, raised to the power n dx equals n factorial over 1 plus 1 times 0 times 1 plus 2 times 0, dot, 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 all the way up to 1 plus n times 0. So on the left-hand side of the equation, that leading term will just equal 1 when we do all the arithmetic there. The integral will become 1 minus x to the 0 over 0 to the n dx. And of course, on the right-hand side, we just have n factorial. So this will then equal the integral from 1 to 0 of 1 minus x to the 0 over 0, all to the n dx. And again, this expression should equal n factorial. Now we still have this something over 0 expression, but this is actually a much more workable form. Because in our integrand, instead of having a number over 0 expression, we have a 0 over 0 expression. So we can consider that expression as a limit of the function 1 minus x to the z over z as z tends towards 0. And we can apply L'Hopital's rule, which tells us how to evaluate these types of expressions that are 0 over 0. So again, we have the limit as z approaches 0 of 1 minus x to the z over z, which will be the same thing as writing limit as z goes to 0, 1 minus e to the log of x to the z over z. And L'Hopital's rule says to find this limit, successively differentiate the numerator and the denominator in the expression. Well, differentiating the denominator is easy. dz just equals 1. And as far as the numerator is concerned, d1 minus e to the log x to the z, dz. 1 is a constant, so that becomes 0. So this equals d dz negative e to the z log x. And now we have to apply the chain rule to do this derivative. So we get negative e to the z log x times log x. Remember here that z log x is just going to be treated as z times a constant. So when we differentiate with respect to z, the constant is the only part that survives there. So we get negative e to the log x to the z. I'm just bringing that z up into the exponent times log x. And then, of course, e to the x and log x are inverses of each other. So we just get negative x to the z times log x. And that negative x to the z times log x is going to be what goes up into the numerator there. And now, having differentiated the numerator and the denominator, we take the limit as z approaches 0 of negative x to the z log x over 1. Negative x to the 0 is just negative 1, so we get negative log x. So finally, after all of that math, we have this expression, the integral from 1 to 0 of negative log x to the n dx equals n factorial. This is our integral expression for the factorial function. So I'll put a big box around that. And that's pretty much where Euler left things. But that isn't actually the integral form of the factorial function that we use today. We're going to make a variable substitution here following the mathematician Legendre. And it's actually very straightforward what we're going to do. Legendre said, let's do the following. We're going to let t in this expression equal negative log of x. Then negative t equals log of x. And we can say e to the negative t equals x. And we'll make a few other remarks here that will be useful. From that substitution, it becomes clear that dt dx equals negative 1 over x. Therefore, dt times x equals negative dx. Or we can say negative x dt equals dx. We're going to use those facts. And then lastly, if e to the negative t equals x, then negative e to the negative t dt equals dx. So we're going to use all these facts here. And when we consider our bounds of integration, these will actually change. Negative ln of 1 equals 0, and negative ln of 0, well, that isn't defined, but it approaches infinity. So the bounds of our integration are these, and we can then write the integral this way, the integral from 0 to infinity. And here's our substitution here, letting t equal negative ln of x. So we get t to the n, and there's our dx expression. So times negative e to the negative t dt equals n factorial. And now because of that negative in the integral expression, I reverse the bounds of integration, and I get the integral from infinity to 0 of t to the n e to the negative t dt equals n factorial. And I put a box around that there because that is our final expression for the integral form of the factorial function. The integral from infinity to 0, t to the n, e to the negative t dt equals n factorial. And now we can finally introduce the gamma function, which is designated with the Greek capital letter gamma. And I believe this convention was also introduced by Legendre. And Legendre found that it was often more convenient to work with n-1 factorial in certain mathematical equations. And so it's very easy to define that. We substitute n-1 into the integral, and we get gamma of n equals the integral from infinity to 0 of t to the n-1 times e to the negative t dt. And that just equals n-1 factorial. And this is really the final result of this video lecture. And again, the power and the beauty of this integral formula is that it extends the factorial function. So it not only agrees with what we would expect the factorial to be for n equals a positive integer, but it actually allows us to define the factorial for terms that aren't positive integers, such as n equals positive 1/2 or negative 1/2. It also gives us the factorial function in an integral form, which can be easier to work with than an infinite product. So that's it for today. I hope you enjoyed this video, and if you did, please like the video or subscribe to my channel, and I'll see you next time.